Hello mathematicians, we're now going to have a look at solving simultaneous equations, or as I prefer to call it, tedium personified. It's an important skill, it's one which you'll use often, but it is very tedious, but it's very mechanical by the same token. So pairs of simultaneous equations may be solved by the following methods. It's probably more important to actually think about what solving equations simultaneously actually means. What it means is that we're looking for the one set of values, well actually there can be more than one. We're looking for the sets of values of the variables which will satisfy two equations at once. So it will satisfy them simultaneously. And the reason it's important is that graphically what this corresponds to is points where curves intersect, and that's an important concept for later in the course. We can apply it with linear and nonlinear equations, and we can use several techniques. So we'll have a really quick look at all of these. Our first technique is substitution. This will always work when one equation can be solved for a single variable. However, it's not always the quickest, as we'll see, but it works for combinations of linear and nonlinear in particular. Our other method, and I'll just mention this now because you will have seen it before, elimination is sometimes quicker, but it usually only works with combinations of linear equations. So let's have a look at these and let's have a look at the process. Now, my biggest fear here is that I haven't left enough space, so I'll start writing small to begin with. Step one is always to write your equations and number them. So I have these two. And if I'm going to solve simultaneously by the process of substitution, I want to make one variable the subject of one of the equations and then substitute it into the other. Now, it's a bit of an art just deciding what you're going to make as the subject. Here, for no good reason, I'm going to make A in the top equation the subject. So from equation 1, what I'll get is that A therefore equals, and that B would come across, and I would add it, so A equals B minus 2. Substitute that into equation 2, and that will give me, in place of A, I'll write B minus 2. So B minus 2 plus B equals 4, so I have substituted. So gather together the B's, I've got two B's there, take that 2 over to the other side, so 2 B's equals 6, so B equals 3. Now I can take that B equals 3 and I can put it into this, or this, or this is probably the most effective, and find the value for A. So therefore A equals 3 minus 2, which is 1. Now, the good thing about solving simultaneous equations, if there is a good thing, is that I can check. I don't always, but I have that option, that I can take this 3 and 1, see whether it makes this true. So 1 minus 3 is negative 2, and 1 plus 3 is 4, so I know that those two are correct. Now over here, I've got y equals x squared, and 2x plus y equals 0. Now I've already got this equation with a variable as a subject, so I'm just going to substitute y equals x squared, so I'm going to substitute that equation 1 in 2. So where the y is, I'm going to put an x squared, so I've got that. Therefore, if I factorise that, x squared outside of x plus 2 equals 0, I can see I get two different possible values, which is not unusual if there's an x squared in there. In fact, it's more the norm. Generally, the number of possible solutions equals the highest power. So x equals 0 or negative 2, therefore when x equals 0, y would equal 0, and when x equals -2, y would equal 4. Now what that corresponds to, just for what it's worth, is if I think of y equals x squared, that's that parabola. 2x plus y equals 0 is the straight line y equals minus 2x, which passes through the origin and has a slope of -2. So it looks vaguely, and most of my drawings are very vague, it looks like that. So here is my 0, 0, this pair of values, and over here is my -2, 4, the other point of intersection of these curves. We didn't need that for this question, we just needed to solve, but that's the significance of it. Now our next option, elimination, works with linear equations, and we add or subtract those equations in order to eliminate a variable. So if we look at our first example, so this was the same one we did up above by substitution. With the equation written like this and the variables lined up underneath each other, we've got options. We can either subtract, so if I took equation 2 from 1, for example, I could get rid of the a's. Or we can add, and I could then get rid of the b's. So it's entirely up to me which option I choose. There's no preference for one over the other, so if the two signs are the same, then we will end up subtracting. If they're different, we'll end up adding. So I'm going to add. So if I do that, 1 plus 2, then a plus a minus b plus b means b is eliminated. -2 plus 4 gives me 2. Therefore, as we found up above, a equals 1. And if I plug that 1 back into either equation 1 or 2, I'm going to find that b equals 3. Now for my next example, sounds like for my next trick, first equation, second equation, it's not nice because I can't just add or subtract. So what I really need to do is to say, well, I'm going to get rid of either x or y. I have to have the same coefficient of the x's or the y's before I can add or subtract. Which is the easiest process to get the same coefficient? Well, the easiest is that if I multiply everything in equation 1 by 5, then I'll have the same coefficients of the y. The more difficult alternative, but just as valid, is to say, well, if I multiply everything in the first equation by 2 and everything in the second equation by 5, I'll have 10 x's here, 10 x's there, and then I'll get rid of the x's. So me being lazy, I'll take option 1, so I'll say equation 1 by 5, and that will give me 25x minus 5y equals 5 times that will be 95. So that will now be equation 3. And I'm going to then add 2 and 3. So for the x's, I'll have 27 x's. The y's will disappear. Y will be eliminated. And y9 has disappeared there. So 95 minus 14 will give me 81, and therefore x equals 3. And once I know that x equals 3, I can plug that back into any of my equations, that one, or that one, and find the value of y. So again, pick the easiest one. So if I look at equation 1, that will give me 5x, which is 15, minus y equals 19. So take that 15 across, minus y equals 4, therefore y equals minus 4. So x equals 3, y equals minus 4 would be the solution to that. And again, pictorially, that means that the point 3, negative 4 is where these two straight lines, that's what linear functions are, where they intersect with each other. And we only expect one solution for these. If we get more than one, we've done something wrong. Okay, so now we're going to take things to a whole new level of tediousness. And we're going to look at solving systems of 3 simultaneous equations with 3 unknowns. So the number of equations corresponds to the number of unknowns. Thank goodness 4 unknowns is not part of the course, or we'd need 4 equations. What we have to do here is to take our 3 equations 2 at a time to eliminate one of the variables, and then we just work with those 2 equations, solve them as we did up above, and then come back and find the 3rd equation. How do you know what to eliminate? Practice. There's no other way. Practice lets you see what might be the easiest combination. In theory, any combination is possible, but some will be quicker, some will be really, really bad. So let's have a look at this one here. I'm only going to do one example for reasons which will become obvious fairly quickly. So, step 1, write them all down. Now, at this point, you are probably already astute enough mathematicians to look at these and say, which one looks the easiest to work with, which variable, and it's C, because it doesn't have any pronumerals in front of it. So I'm going to try to take equations 1 and 2 and eliminate C, and then equations 2 and 3 and eliminate C. Or maybe 1 and 3 and eliminate C. I just need 2 at a time. So let's take equation 1 and equation 2. What would I have to do? I would add those. So where 1 plus 2 will give me, so the a's will add to give 2a, the b's, minus b plus 2b will give me a b, and a c plus minus c means the c's will disappear, and a 7 plus minus 4 will give me 3. So I've got an equation with only 2 unknowns. Number it to keep track of it. Now look at some other combination. So as I said, I could do 1 and 3 or 2 and 3. 1 and 3 is probably the easiest because I can use exactly the same technique. I can just add them. If I used 2 and 3, I would have had to subtract them. So if I take 1 and 3, then that will give me 4 a's altogether, minus 2 b's, the c's are gone, and 7 and 3 are 10. So that gives me equation 5. So over here on the right hand side, I have 2 equations and 2 unknowns. I can solve those. Unfortunately, I'm going to have to adapt those a little bit. So if I decide I'll get rid of A, then if I take equation 4 and multiply it by 2, then that will give me 4a plus 2b equals 6. So that will be now equation 6. You can start to see why I'm numbering them. And if I then take equation 5 minus 6, that will give me 4a minus 4a, minus 2b, so minus 4b, and 10 minus 6, which is 4, therefore b equals minus 1. Okay, once I know that b equals minus 1, I can go to this or this or this and find a. So let's plug it back into equation 4. It looks like the simplest one. So 2a plus minus 1 equals 3. So 2a equals 4, a equals 2. So just a quick double check that they are actually true for these ones here before I get too involved. So 2 plus minus 1, sorry, 2 2's, 4 plus minus 1 gives me 3, so that's okay. And 8 minus 2 times minus 1 does give me 10. So at least they're okay if these are okay. So then all I need to do is to plug those two back into any one of those three up there and find C. So equation 1 looks easiest to me again. So in equation 1, A equals 2 minus B, so that's minus minus 1, plus C equals 7. Therefore, C equals 7 minus 3, which is 4. Okay, that actually wasn't as bad as I thought it could be, but I'm sure we'll manage to find some bad ones. Okay, have fun with the exercise.